Chapter 3, Physical Principles of CT. So real quick, we'll discuss some of the limitations of film-based radiography and conventional tomography. In film-based radiography, there is superimposition of anatomy, and remember this is difficult to see the detail of structures since they are laying over one another. There's also the qualitative process, and it does not involve the quantitative process, which makes objects look the same, although they are different. Take a look at Figure 3.3 to see how the textbook lays out this issue. Film-based radiography is also bad at demonstrating slight differences in subject contrast. And in film-based radiography, the contrast cannot be adjusted after the film recording. So in conventional tomography, the superimposition of anatomy is decreased, but blurring isn't completely removed. The superimposition blurs out the unwanted sections of anatomy and keeps desired anatomy in focus. However, sometimes this is difficult to obtain. Also, the degradation of image contrast occurs due to the presence of scattered radiation created by the open geometry of the X-ray beam. And also, in conventional tomography, just like in film-based radiography, it is bad at demonstrating slight differences in subject contrast, and contrast cannot be adjusted after the film is recorded. So how can CT help overcome these limitations? CT minimizes superimposition, one of the big drawbacks of film-based radiography and conventional tomography. X-rays are transmitted through specific cross-sections of the patient, which removes the problem of superimposition above and below the specific cross-section or slice of tissue being looked at. The beam of X-rays is highly collimated into a very narrow beam that only passes through the cross-section of tissue to be imaged. And this procedure minimizes scatter radiation and also improves the contrast of the image. When the X-ray beam passes through the patient, it strikes special electronic detectors positioned opposite the X-ray tube. These detectors are quantitative and can measure very small differences in tissue contrast, whereas the film screen detectors cannot, since they are only qualitative. Additionally, the analog signals from the electronic detectors are first converted into digital data and are then processed by a digital computer that uses special algorithms to reconstruct an image of the cross-section of anatomy. CT can be described in terms of physical principles and technological considerations. The physical principles involve mathematical concepts to understand the way the image is produced, and the technical considerations involve the practical implementation of scientific and engineering principles, such as computer science and technology. The physical principles and technology of CT include 3 processes that we discussed in Chapter 1: data acquisition, data processing, and image display, storage, and communication. But we will go into a little more depth right now regarding all 3 processes. So with data acquisition, remember this refers to the systematic collection of information from the patient to produce the CT image. This happens by slice data acquisition, which is when data is collected through different beam geometries to scan the patient. So basically the tube rotates around the patient and collects data from the first slice, then the tube stops, and the patient moves into a position to scan the next slice. This continues until all slices have been individually scanned. In volume data acquisition, special beam geometry called spiral or helical geometry is used to scan a volume of tissue rather than one slice at a time. So with this type of acquisition, the tube rotates around the patient and traces a spiral or helical path to scan an entire volume of tissue while the patient holds a single breath. This method generates a single slice per 1 revolution of the X-ray tube, and it often is referred to as a single slice spiral helical speed performance, or SSCT. In multi-slice spiral helical imaging, or MSCT, this generates multiple slices per 1 revolution of the tube and makes imaging even faster. And it started with a 4 slice, and now there is a 320 slice commercially available. So scanning is when the tube and detectors rotate around the patient and the different intensity readings are collected. Detectors measure the radiation transmitted through the patient from various locations, and relative transmission or attenuation measurements are calculated. There is a formula for relative transmission, and it is the intensity of the X-rays at the source divided by the intensity of the X-rays at the detector times the log. The relative transmission values are then sent to a computer and stored as raw data. Then the data is reconstructed by transmission measurements, and there's a large number of these needed. Usually several hundred views are obtained, and each view is made of a number of rays, and the total transmission measurements for each scan are given by another formula, which is the number of views times the number of X-rays in each view. Remember, this is the total number of transmission measurements, which is this bottom formula right here. The issue CT is determining the attenuation in the tissues and using this information to reconstruct an image of the slice of tissue. The solution to this problem is a little complex and involves mathematics, physics, and computer science. To even begin to understand, you need to have an understanding of attenuation of radiation in general and attenuation in CT in particular. In attenuation, this is the reduction of intensity of the X-ray beam as it passes through an object. Some photons are absorbed by the body and others are scattered. And in CT, it depends on the effective atomic density, or the atoms per volume, the atomic number, represented by Z, of the absorber, and the photon energy. There are 2 types of radiation beams, and you should know how each of these are attenuated. There's a homogeneous beam, where all photons have the same amount of energy, and this is laid out in figure 3.8 of your book. Each section of the absorber attenuates the beam by equal amounts, so the quantity of photons is reduced. And in a homogeneous beam, the quality of the beam, or the beam energy, does not change. So in other words, the kiloelectron volts does not change. If the starting beam energy is 100 keV, then the transmitted photons all have an energy of 100 keV. So the Lambert-Beer law, we won't go into too much detail, but it's located right here on your slide, and it describes what happens to the photons as they travel through tissues according to the following formula. There's also a heterogeneous beam where all photons have different energies, and this is laid out in figure 3.9. Lower energy photons are absorbed as they pass through the body, which then allows for the higher energy photons to continue to pass through the body, which then results in the penetrating power of the photons to increase and the beam hardening to increase as it passes through. The way that the X-ray tube and detectors are arranged to collect transmission measurements describes data acquisition geometry of the CT scanner. And there are 2 types. Take a look at figure 3.10 in your book. The X-ray tube and detectors are coupled and rotate 360 degrees around the patient to collect transmission measurements by using a fan beam of radiation for the first type. This is most common in modern CT scanners that you see today. Then there is another type where the X-ray tube rotates 360 degrees around the patient and is positioned inside a stationary ring of detectors, but the X-ray beam is still a fan beam. So this image right here is the first one I described, the first type, where the tube and detectors are actually coupled together here, and then they together rotate around the patient. And then the picture right here describes where the X-ray tube rotates 360 degrees around the patient, but it's inside the stationary ring of detectors right here. Data processing basically involves the mathematical principles of CT and is essentially a two-step process. So within this two-step process, first the raw data undergoes pre-processing, and some corrections are made and reformatting of the data occurs. Also in this two-step process is the image reconstruction that occurs. The scan data, which represents the attenuation readings, are converted into a digital image characterized by CT numbers. And this conversion is done by reconstruction algorithms. CT numbers are related to the linear attenuation coefficients of the tissues that make up the slice. Each pixel is assigned a CT number, and it is calculated by this formula right here. You will often hear the CT number be referred to as the Hounsfield number or the Hounsfield unit. And on the H scale, water has a CT number of 0. Bone has a CT number of plus 1,000, and air has a CT number of minus 1,000. The computer calculates the CT numbers, which can be printed as a numerical image, and the image must be converted into grayscale image, which is more useful to the radiologist. The brightness levels correspond to CT numbers, so the higher numbers are white and the lower numbers are black, and all numbers in between are shades of gray. Linear attenuation coefficient is affected by several factors, including energy dependence, which is the energy of the radiation. And the photon energy also affects CT numbers since they are calculated on the basis of the attenuation coefficients. The attenuation coefficient changes when the beam energy changes. In CT, a high kV technique, like 120, is generally used in order to reduce the dependence of attenuation coefficients on the photon energy, reduce the contrast of the bone relative to the soft tissues, and produce a high radiation flux at the detector. CT numbers may vary because of their energy dependence. This is very important for numbers to be accurate and reliable as to not to lead to a misdiagnosis. The final step in the CT process involves image display, storage, and communication. So after the image has been reconstructed, it exits the computer in digital form. This then must be converted into a form that is suitable for viewing and that is meaningful to the rad. The image is displayed on a monitor, which is usually a cathode ray tube or a liquid crystal display, and it is influenced by physical characteristics such as the luminance, noise, dynamic range, and the resolution. The resolution is a very important physical parameter of the grayscale display monitor and is related to the size of the pixel matrix or the matrix size. The display matrix can range from 64 by 64 to 1024 by 1024. High performance monitors can actually display 2048 times 2048 matrix. A CT image is composed of a range of CT numbers representing varying shades of gray. The window width is the range of CT numbers, and it controls image contrast. And then the window level is the center of that range, and the window level actually controls image brightness. The window width and window level alter the image brightness and contrast, and they're located on the control console. So the window width can equal 2000 and the window level equals 0, and this can show the entire grayscale. And it makes it hard for the observer to see the difference in small details. And this is since the human eye can only perceive only about 40 shades of gray. With windowing, this is the process of changing the CT image grayscale. As the window level increases, the image goes from white to dark, as the image contrast changes for different values of the window widths. And different windows are used for different scanning procedures and protocols, and some examples include the bone window for when imaging bones, mediastinal window for when imaging the structures in the mediastinum, and the lung window when imaging the lungs. So the size of the image matrix is chosen by the tech before the imaging occurs, which is done by selecting the field of view. The field of view is a circular region from which the transmission measurements are recorded during scanning, and this is also known as the scanned field of view. The matrix is placed over the scanned field of view to cover the slice to be imaged during the data collection and image reconstruction. The radiation beam then passes through each voxel, and remember it is now a voxel instead of a pixel because it has the dimension of depth. And the CT number is generated for each pixel in the displayed image. The pixel size is represented by D and can be calculated from the field of view divided by the matrix size, this formula right here. And it generally ranges from 1 millimeter to 10 millimeters on most scanners. The voxel size depends on thickness of slice, the matrix size, and the field of view. In isotropic imaging, the length, width, and height of the voxel dimensions are all the same. Each pixel in the CT image has a range of gray shades, and these numbers are represented as bits. Remember, we discussed this a little in Chapter 2. So the CT image can then be characterized by the number of bits per pixel. CT images can have 8, 9, 10, 11, or 12 bits per pixel. Bit depth is the series of bit planes, and the numerical value of pixel represents the brightness of the image at the pixel position. For example, a 12 bits per pixel CT image would represent CT numbers ranging from -1000 to 3095 for a total of 4096, or 2 to the 12th power, shades of gray. So as we all know, the ultimate goal of the CT scanner is to produce a high quality image with minimal radiation dose and little discomfort to the patient. The technology of a CT scanner encompasses a number of subsystems that demonstrate the flow of data through the CT system, which we will now discuss. The subsystems are shown in figure 321 of your textbook, and the data flow of a CT scanner includes the X-ray tube, power supply, the cooling system, the collimators, the detectors, and much more. I'll just take you through this flow chart right now. The scan parameters are first set, and then the tube rotates around the patient to collect the raw data. The data is transmitted and reference beams are converted into the electric current signals. And then the logarithmic amplification occurs, and this is where the relative transmission readings are changed into attenuation and thickness data through the equation covered on page 55 in your book, equation 3.2. Data preprocessing then occurs, including subtraction of the reference detector value. And then the reformatted raw data is further corrected by computer software. And then the convolution is performed on the data. And then the back projection reconstruction algorithm reconstructs an image of the internal structure being scanned. And then the digital image is finally displayed or stored. So compared with radiography and conventional tomography, CT obviously offers some advantages. One of these is excellent low contrast resolution is possible, and this occurs from a highly collimated beam and the more sensitive detectors to measure radiation transmission. Then there is the contrast scale that can be varied, and the volume data acquisition can also be taken in a single breath hold instead of multiple breath holds. Digital image processing is available, and CT can also produce 3D images, which improves the diagnostic interpretation of the images. However, CT still has its limitations, which include poor spatial resolution and a higher dose than radiography. And it's difficult to image anatomic regions where soft tissues are surrounded by large amounts of bone because artifacts may occur. Metallic objects on patients produce streak artifacts on images, and other artifacts also can be seen and produced for other reasons.